Hello and welcome to today's class. So, in our last lecture I had discussed about the type of data you acquire from a given experiment and the ways and means of presenting that data. So, in today's class we will see how you from that data you can extract some quantitative parameters to distinguish between two experimental conditions and say whether those differences are significant or what kind of conclusions can you draw by looking at the data. So, before we get started I would like to do a brief recap of what we had discussed in last class. So, in the last class I had discussed about the types of data, which would mean categorical data, which is more qualitative in nature, or quantitative data. Even within the types of data, in quantitative data you might have discrete variables like the number of visits to a clinic, so on and so forth, or continuous variables like the time it takes for a student to solve a problem. Okay. Then we discussed about the types of plotting, and for expressing for standard representation of qualitative data is using pie charts or bar charts. But the caveat is that these kind of charts you can only plot when the number of conditions or the number of distribution is not widely distributed. In other words, if you have in a pie chart, if you have to show 200 conditions, then it is impossible to fathom any sense from that plot, because everything has to be represented in terms of a circle. Okay. Then we talked about the histogram. It is one of the most widest used distributions. Okay. And how you go by converting data, raw data, by using frequency tables. You make bins, you make frequency tables, so that you can put that data into some form, and then you plot in terms of values and their frequency, and you get what is known as a histogram. Right. So, this is a sample representation of a histogram. Right. We can have this is my frequency axis. Okay. This is my variable x, let us say. This vertical axis my frequency, okay, and this is how I can plot them. Now, these frequency axis can be plotted in absolute terms or in relative terms, and this relative frequency is important when you are comparing between two separate experiments or two different conditions and the number of data points is not the same. Let us say in one case you have obtained the data for total of 50 points, and in the other case there are 100 points. So, if you were to put that in the same frequency data, the plot might look. So, if I were to overlay on this existing plot a different plot, it might look like this, but in reality if you normalize, so if you actually normalize this data, okay, so what you might have, your data might actually look like this. Okay. So, this you have relative frequency, where you divide with respect to the total number of observations. Okay. After histogram, we discussed about line and scatter plots. These are widely used. Okay. So, you just depending on your variables, let us say you have two variables x and y, and you are plotting how y is varying with respect to x. You can put them as scatter plots, where they are individually each point is the xy representation in 2D. But of course, with scatter points you can convert it into line plot only if it makes sense. If these data have some very clear trend that it can be approximated by a line, then it makes sense to make it as a line plot. I also briefly discussed about this double y plots, where you have two, let us say you have three variables x, y, and which are changing with respect to a variable z. Then you can plot let us say x and y with respect to your variable z, and let us just say that let us take a simple example where z is time and x and y are two variables which are varying with time, and we want to see how x and y correlate. So, as per the plot I have drawn, as x decreases, so in our case z is my time axis, at x decreases with time, y increases with time, which tends to say that they are inversely correlated. Okay. So, next thing I wanted to talk about, so in terms when you are making the plot, few things to keep in mind. You must label your axis appropriately, you must choose appropriate units. So, for example, let us say we are talking about cell speed, you can report, or any speed you can report in micron per minute, micron per hour, meter per minute, meter per hour, so on and so forth. depending on what you are measuring and what is the minimum amount you can measure in accurate manner. Okay. So, that also brings us that you want to choose the appropriate range. Let us say you are seeing a population explosion and the maximum value you choose for your y axis, right. So, if I go to the example, let us say this is time and this is my population. Okay. If I want to convey that my population is really increasing with time and I choose my y range such that my curve only looks like this, then what I want to convey does not flow with the way I have plotted the data. Much rather what I should do is I should plot the same curve with, so if this is my max value, so I can choose this max value as reasonably high, so I can really see a nonlinear growth in the way the population is expanding, as opposed to choosing an arbitrary large value for the y axis. Okay. The other thing, important thing to note is when you have large variations in data. Let us say most of your values I am just plotting, let us say this is my time axis and this is my x axis, okay, and x values are either you have very low values 0.1, 0.2, 1, and then suddenly the next value goes to 40, 50, 100. So, it is very difficult to represent all these values of x in the same plot. So, there are two approaches. So, what you do, you either insert a break in the axis. So, let us say my 0 to 1 is in one graph, and the next point starts from 35. So, my 40 point will rise somewhere here, and my let us say if this largest value is 0.8, it will be somewhere here. So, I can see both these points on the same axis. The alternative to that is to plot over a wider range, and what you do is you show a smaller range. Let us say this is from 0 to 100 and this is from 0 to this vertical axis is from 0 to, this is your time axis. Okay. So, this vertical axis is from 0 to 100, but the inset is only from 0 to 1. So, here you can have these extra points and then you can clearly see how they vary in y axis. So, this is using insets and this is using breaks. Okay. So, let us just begin today's lecture with one example. Okay. So, this is sample representation of data of 10 students in 2 exams, okay, and we want to find out how we should represent this data. So, I presume it is reasonably clear to most of you that since it is x and y for 10 students, then what you can do is the easiest way to plot this data is using a scatter plot. Okay. So, you can plot using scatter, and for each point you can see, so say 61 and 49 and so on and so forth. So, let us say your maximum value is in the range of 0 to 100, 0 to 100, okay, and then accordingly you can put individual points and see how these performances are correlated. So, your aim might have been to see that how the students are performing across different exams, and these are in 2 different exams, so perhaps 2 different subjects. So, if you see a very positive correlation, so let us just say one simple case that you have sorted this data and you have plotted them separately such that, so here I have just randomly plotted, but you have plotted in such a way that the student, so this is the student with the lowest score in exam 1, he or she also scores the lowest score in exam 2. So, they have the lowest score. So, if a curve, if you sort the data and replot like this, it conveys the message that the students have reasonably, they vary in their standards, and the student who is good is consistently good, and that is the reason why high score in exam 1 also translates into a high score in exam 2. And similarly, for the student who is weak, low score in exam 1 is also closely related to a low score in exam 2. Okay. So, let us take another example. Okay. So, we now have, this is the data for RBC counts of a healthy individual measured in 15 successive days. Okay. So, it has units of 10 to the power 6 cells per ml per microliter. U-liter is short form for microliter. So, what you can see is you can have these following values. So, the question is how should we represent this data. So, if I were to look at the values which are occurring, I have 4.9, I have 5, I have 5.2, I have 5.3, I have 5.4, and I have 5.5. Okay. So, these are the values and I can plot their frequency. Okay. 4.9 appears twice, 5 appears 1, 5.2 appears 1, 2, 3, 4 times. Okay. 5.3 appears 2 times, 5.4 appears 3 times, and 5.5 appears once. Okay. So, the very fact that I have actually converted into frequency plot would mean that eventually you would plot this data as a histogram. So, these are your individual values 4.9, 5, so on and so forth. This is your 5.5 value, and what I can see is, so if I were to, so this is my 2, 1, then I have a maximum of 4, then I have 2, 3, 1. So, if I were to actually connect these data, so my curve would look something like this. So, the histogram looks something like this. Okay. Now, whether or not it is so, this is too few numbers, so it is difficult to comment on it, but if let us say I ask you the following question, let us say in today's course. So, this is your values for the last several days and today's score is 5.7, is it unusual? So, you can clearly see from your existing histogram that there is no 5.7 value. So, one would argue that 5.7 is a little bit unnatural, maybe you are suffering from some disease or infection. So, it warrants a doctor's examination. Okay. So, let me take another example. Okay. So, imagine we have I actually take the statistics of average students' height in a class. Okay. And I do it on 3 successive days, and this is, so this is the plot of height and relative frequency. On day 1, this is my distribution, on day 2, this is my distribution, and on day 3, this is my distribution. So, this is mind you, it is not from 3 different populations, it is from the same population, right. So, and it is a little bit baffling, as you can see that there are some overlapping regions, but the curves look reasonably different from each other. So, what are the qualitative aspects of these curves which are different? What I can clearly see is, if I were to look at the maximum in peak height, so for which you have the maximum number of observations, it is at this value to the left on day 1, to the right on day 2, and to the middle on day 3. Now, if I were to imagine that on an average your population consists of boys and girls, and on an average boys are taller than girls, then it is possible that on day 1 you had a greater number of girls present in the lecture, on day 2 you had a greater prevalence of boys attending the lecture, and on day 3 there is a reasonably equal distribution or equal fraction of the boys or the girls who were present in the class. Okay. So, this begs the question that how can I capture this data? Okay. How do I go about in trying to capture this data? And that brings us to the next topic, that how can I come up with numerical measures to describe data. And perhaps the most popular one, the widest used one, is arithmetic mean, which most likely all of you have heard, right. So, average or arithmetic mean, the way it is defined is, let us say I have a set of variables x1, x2, x3 dot 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 n variables xn, right. Now, n, so this is my sample. Okay. I have drawn a sample of n from a population y1, or let us say x1, x2, x capital N. This is my population. Okay. So, just to stop any confusion, let me write them as y1, y2 and yn. So, essentially you have derived a sample of small n is less than capital N. Okay. And we want to know what is the arithmetic average. Okay. So, as most of you are perhaps aware, mean or sample mean is defined by this variable called x bar, which is nothing but x1 plus x2 plus x3 plus up to xn divided by the number of observations, which is n. Okay. So, in simple language I can also write it as in a compressed form, I write summation x I and I is equal to 1 to n, which means, so you put the summation sign here and it goes from I is equal to 1 to I is equal to n. So, this is for I equal to 1, it is x1, for I is equal to 2, it is x2, so on and so forth. So, this is your definition of sample mean. Similarly, I can define my population mean. So, it is typically used, mu is a term which is used to define the population mean. It is similarly by yi by capital N. So, sometimes, many times you will see we just put the summation sign without actually writing the limits, but it is understood when we do not put the limits, it is from the first value to the last value. So, this is from the first value to the last value. Okay. So, in simple speak, I would then, so I can accordingly simplify x bar as summation x I by n, and this is summation y I by capital N. Okay. So, now let us do some transformations, simple thing. So, imagine I had this variable x, okay, and I define this variable y, which is nothing but a times x, okay, and I want to know what is the relationship between x bar and y bar, okay, how are they connected. So, how do I go about it? So, what I should do is I can write, so if y is equal to a x, so this would mean my y1 is equal to a x1, y2 is equal to a x2, y3 equal to a x3 dot yn is equal to a xn. Okay. So, then we can derive, so what is my then definition of y bar? Y bar has to be nothing but y1 plus y2 plus y3 up to yn by n. So, y1 is nothing but a x1 plus a x2 up to a xn by n. I can take a common and it is x1 plus x2 up to xn by n. Okay. So, if this is, so let me write it in a new page, my y bar is nothing but a times x1 plus x2 up to xn by n, which is nothing but this is nothing but x bar, right. So, x1 plus x2 up to xn by n is x bar. So, y bar is nothing but a x bar. So, this tells you that when you have a prefactor which is multiplied on a variable x, then the average of the new variable y is simply the prefactor multiplied by the average of x. Okay. Now, let us do another simple transformation. Imagine y is nothing but c plus x. Okay. So, I want to ask what is y bar and x bar, how are they related. So, what you can do the same exercise, you can do the same thing, but y bar is now c plus x1 plus c plus x2 plus c plus xn by n. Okay. So, if that is so, so what I can take in my definition of y bar, I can take c common, but c is 1 plus 1 plus 1 n times, then you have x1 plus x2 plus xn and this whole thing divided by n. Okay. Now, this 1 plus 1 plus 1 n times is simply n. So, this gives me the formula c plus, and this remaining thing is x bar. So, y bar is c x bar. Okay. So, when you have a constant to a variable x added, what you can do is you can simply put y bar is a constant plus the x bar. Okay. So, if I were to generalize these two rules, so if I have a variable y which is c plus a x, then I can write the formula y bar is c plus a x bar. Okay. So, these this is what the three rules of transformation is. So, let us apply this transformation to a sample example. So, imagine these are the test scores of the 20 students, right. So, if I write down like this 61, 93, 87, 42, 55, 67, 82, so on and so forth. Okay. So, I will only take these following numbers. Okay. So, now let us say this is my design variable x. So, I want to add I want to find out x bar. Now, what I see the range. So, if I just look at these few numbers, this is the smallest, okay, and this is the largest. Okay. So, what I can do is, if I define, so it boils down to the question, how should I define y, so that it will be convenient for me to calculate this average using this using these transformations. So, what you can do, one of the transformations which you might think of doing is dividing by 10. So, everything becomes 6.1, 9.3, 8.7, but still you have to add lot of the fractions, which is not so convenient if you are doing it by hand. So, easier alternative is to define y. So, if I define y, so my smallest is 42, largest is 93. Let us choose y as x minus some value which is in the middle of 40 and 90. Okay. So, which is 65. 65 is nothing but average of 40 and 90. So, 40 plus 90 by 2 is 65. If I define y as x minus 65, then this guy becomes minus 4, this guy becomes plus 28, this becomes plus 22, this becomes minus 23, 55 means minus 10, 67 means 2, 82 means 17. Okay. So, I can add these numbers up, this is much more reasonable than adding much bigger numbers. So, what you can see is, so 22 and 23 is almost cutting each other out. So, these two put together is plus 1, and here you have, so 28 plus 2 30 minus 10 20 plus 17, 20 plus 17 plus 1 18, 38 minus 4. So, 38 minus 4 is 34. Okay. So, you can calculate the x bar, which is nothing but your y bar is nothing but 34 by, let us say, number of observations here 1 2 3 4 5 6 7, which is roughly equal to 5. If I approximate y bar by x bar, then I can look at this equation and I can say how is x bar then. So, if x bar is nothing but y bar plus 65. So, x bar, so I can then find x bar as nothing but approximately 70 is my average. Okay. So, without using calculators, you can use simple transformations to make them go from one to other, and it is make it easier for you to do this. Okay. We could have, and please remember that this value of 65 is not a magic number, this we chose based on the range of the numbers. Okay. So, one simple rule of thumb you can do is, if you have all these numbers, let us say x1, x2 dot dot xn, you first sort them from lowest to highest. Okay. And let us say we call that y1, y2, so on and so forth, yn. So, in our previous case y1 was roughly 42 and yn is roughly 93. Okay. So, what we can now do, we can have this transformation y is equal to x minus c, or this c that we define, c is nothing but what we chose was average of y1 and yn. Okay. So, the idea is that when you choose something in between and apply this transformation, so if I were to look at this again, so if I choose a value in between, I will get some numbers which are negative and some numbers which are positive, because 65 is roughly in the middle of this range. And when I have negative and positive, then they kind of cancel each other out and you get a lower number. So, we want to get to as low a sum as possible that we can directly compute the total sum by hand, and then accordingly we can apply this transformation. So, this is the way to go about it. You can roughly you sort the numbers from lowest to highest, you identify the numbers and you roughly. So, again we did not put c exactly as 42 plus 93 by 2, because again the process would have been much more difficult to do by hand. We wanted an approximation which we can, which is easy to implement and we can see by hand what we are doing. Okay. So, let us just take one more example, which is the next example. Okay. So, again you see that you have you have this entire range of numbers which goes from, so this is body mass indices, it goes. So, if I look through the screen, my lowest, the smallest number I have is probably 18.3. So, smallest number is 18.3. So, this is my smallest. The largest number is 29.1. Okay, 29.1. Okay. So, then my, as per this, my average is going to be 18.3 plus 29.1 by 2. So, 29 and 18 is 47, 47.4 by 2 is roughly equal to 48. So, it is 24. So, your average is roughly 24. So, you can then add it up. So, if I look at this score again, so my 18.3 will give me a value of 18.3 minus 24, while this 29.1 will lead minus 24 will give me roughly 5, and this will roughly minus 6. So, you see that these two numbers, if I add up, then I will get a value which is close to 0. In this way, we can make use of transformations to make our life lot easier, particularly when we are not working with a calculator. So, with that, I would stop in this lecture. So, summary, I would summarize by saying that arithmetic mean represents one of the simplest ways of representing data, or extracting some quantitative metric to characterize your data, and then using basic transformations you can simplify and do things by hand to find out what is the arithmetic mean of your given data set. So, either y is equal to c plus x, or y is equal to cx, or y is equal to a plus cx are three simple transformations which you can do. So, imagine if your numbers were 100, 200 like that, then by 100, dividing by 100 and making it into 1, 2, 3 would be one simple way. With that, I thank you for for your cooperation, and I look forward to meeting you in the next lecture. Thank you.